Hi everyone, I'm Kangning Wang from Duke University, and today I'll be presenting our work, Online Stochastic Matching with Edge Arrivals. It's a joint work with Nick Gravin and Zhihao Gavin Tang from Shanghai University of Finance and Economics. There are many real-life problems relying on the model of online bipartite matching. For example, in the job market, the employees are matched with the positions. In an online marketplace, the sellers are matched with the buyers. In many of these applications, the environments evolve over time, and online decision-making is required. Since a seminal paper of Richard Karp, Umesh Vazirani, and Vijay Vazirani, there has been uncountable work on this topic of online bipartite matching. This KVV paper considers the vertex arrival setting, where one set of vertices are offline and the other set of vertices arrive online. In our work, we consider another natural and well-studied setting of edge arrivals. In this setting, the vertices are offline, but the edges arrive online. As a motivating example, in the job market, the potential employees and the positions might be known upfront, but the availability information of an edge, that is, whether an employee can take a certain position, is updated over time. In this setting, when an edge appears, we need to decide whether to match its endpoints. And if not, then the edge is lost forever. Our goal is to maximize the number of matches, comparing against the offline optimal. One natural algorithm for this problem is greedy. The greedy algorithm simply matches every arriving edge if its endpoints are available. It is immediate that greedy outputs a maximal matching, and thus gets at least half as much matches as the optimum. On the other hand, this bound of 0.5 competitiveness is actually tight. In this example, the edge U1 V1 arrives first, and greedy matches U1 with V1. Later, the edges U2 V1 and U1 V2 arrive, but greedy cannot choose either of these, since U1 and V1 are now unavailable. However, the optimum can obviously skip the first edge U1 V1 and match U1 V2 and U2 V1. Therefore, greedy only gets one match, but the optimum gets two matches. Now, a natural question arises: can any algorithm beat greedy? In a Fox 19 paper, Gamles, Kapralov, Maggiore, Svensson, and Voits show that no algorithm can give a better competitive ratio than greedy when the edge arrivals are adversarial. This motivates us to put restrictions on the arriving edges. In our work, we consider a stochastic setting or a Bayesian setting where each edge has a predetermined probability to appear. Formally, each edge E independently realizes with probability PE, and the online algorithm knows every E and PE upfront. We ask again in this new setting, is there an online algorithm giving a better competitive ratio than greedy? It turns out the answer is yes. In our work, we show that a simple algorithm, which we call green and greedy, beats greedy and gives a competitive ratio of 0.503. To familiarize ourselves with the setting, we first present our Hartmann's result. No online algorithm can be better than 2/3 competitive. Consider the following example of a bipartite graph. The red edges arrive first, and each realizes with probability 1. The dashed blue and dashed green edges arrive later, and each realizes with probability half. In this example, the offline optimum is about 1.5n when n is large. To prove this, using concentration bounds, we can see that about 0.5n blue edges and 0.5n green edges realize. We select all those edges and match the remaining 0.5n nodes in L1 and 0.5n nodes in R1 with the red edges. Therefore, the offline optimum is at least about 1.5 times n. However, the expected performance of any online algorithm is at most n. To see this, suppose it chooses k red edges. Then there are only n minus k free nodes in L1 and n minus k free nodes in R1 after all red edges arrive. Thus, it can only get 0.5 times n minus k blue edges and 0.5 times n minus k green edges in expectation. The expected number of total matches is thus n regardless of k. Therefore, no online algorithm can be better than 2/3 competitive against the offline benchmark. Now we introduce our proof of 0.503 competitiveness. Firstly, we need a good upper bound for the offline optimum. We will use the idea of gameless Hill and Svensson. Let xe be the probability of selecting the edge e. The performance will then simply be the sum of xe's. We put the following constraint on each vertex v. For any set f of edges adjacent to v, there is a match in that set, only if there is a realized edge in that set. As gameless, Ko, and Svensson showed, the LP can be solved in polynomial time. We use a simple algorithm called pruning and greedy. It first deletes some edges or decreases their realization probabilities. Then it uses the greedy strategy. An immediate first attempt would be to decrease each PE to XE, where PE is the realization probability and XE is the LP solution. It turns out that this decrease is too aggressive, and we cannot beat 0.5 in this way. Instead, what we do is to decrease each PE to YE, where YE is the minimum of PE and 1 minus e to the minus CXE. The optimal parameter C turns out to be about 1.7. When XE is small, 1 minus e to the minus XE is about C times XE. So we are decreasing PE to the minimum of PE and C times XE. This pruning method can be viewed as a less aggressive version of the previous one, which decreases PE to XE. The competitive ratio of pruning and greedy is at least the solution of this mathematical program. We fix a single vertex and look at the edges adjacent to it. In the objective, the denominator is the offline optimum. The numerator serves as a lower bound of the performance of pruning and greedy. This is achieved after some algebraic manipulation, and we will omit the details here. After getting this mathematical program, the rest of the proof focuses on characterizing the worst-case sequence of XIPIs. This part is highly technical and we won't go too deep into the details. Instead, we state some major steps. We now characterize the worst-case solution of the mathematical program. Firstly, Xi's can be the same number that goes to 0, achieved by dividing each edge into several edges with smaller xi's. Next, we show that yi's are decreasing. Otherwise, we can adjust the sequence to make the objective worse. After this, we show that there should be a threshold theta, so that yi takes the value of c times xi before the threshold, and takes the value of pi after the threshold. Finally, we notice that the last set of constraints, that the sum of xi's should be at most 1 minus the product of 1 minus pi's, should be tight for any suffix after the threshold theta. These structural lemmas allows us to calculate the optimal solution of this mathematical program, which turns out to be 0.503, where c equals 1.7. This is better than 0.5 achieved by greedy, and we are dead. As another result, we show that greedy performs well in the so-called log normalized to regular graphs. Log normalized to regular graphs are equivalent to two regular graphs when the realization probabilities are small. In general, we can subdivide each edge into several new edges with smaller realization probabilities. We show that greedy is 0.552 competitive in such graphs, even against the stronger benchmark of the number of vertices on one side. Therefore, if a graph contains a log normalized to regular subgraph, then we can prune the rest of graph away and keep a two regular subgraph. And we can use greedy on this subgraph to get a better competitive ratio of 0.552. Interestingly, when C goes to infinity, greedy is no better than 0.5 competitive for C regular graphs. Now we present some related models. In the stochastic probing model, the edges are associated with probabilities of realization. An online algorithm can probe the edges in any order and pick an edge if it exists. This is equivalent to probing in any order and then deciding whether to pick, since an algorithm can always postpone probing an edge if it doesn't plan to pick it. Therefore, this model is easier than our problem, in the sense that any alpha-approximate algorithm for our setting is at least an alpha approximation in this setting. It turns out, even when the edges have weights, there's a 1-1/E approximation algorithm for it. Another line of work is the profit inequalities for bipartite matching. It's the same setting as ours, except the edges have values drawn from given distributions. In our setting, the distributions are restricted to Bernoulli. In 2012, Robert Kleinberg and Matt Weinberg considered the problem of matroid intersection, which implies a 1/6 competitive algorithm for the setting of bipartite matching. In 2019, Nick Gravin and Wang specifically considered this problem and showed a 1/3 competitive algorithm and a 4/9 Cartman's result. Later, Tomer Ezra, Michal Feldman, Nick Gravin, and Zhihao Gavin Tang improved the competitive ratio to 0.337. That's all I have today. Thanks for your attention.